right, so today we're going to be talking about adders in Logisim, and specifically three kinds of adders: half adders, full adders, and then the 4-bit adders. So here we have the half adder. We have two inputs and then two outputs. Okay. So these outputs are in binary, they are weighted with C being the most significant bit as being the least significant bit. A and B, however, they aren't weighted, and it doesn't matter what order they are in. They are just counted and added together. So say if we have 0, 0, we get an output of 0. If we have 1, then we get an output of 1 here, specifically 0, 1. Same if it was B, 0, 1. Doesn't matter which order, because these inputs aren't weighted at all, but these are. And if you have both of them turned on, then we get an output of 2. Most significant bit here is in the 2 position and is output as 1, 0, which is 2. So let's go ahead and test the full adder. The full adder is a combination of two half adders. And here you can see these half adders are represented in a box, 2 inputs, and there's our 2 outputs. So this is what is known as a subcircuit. This half adder has exactly this circuit built into it, just a lot more condensed down subcircuit. So with this being a full adder, we have 3 inputs. Again, these aren't weighted at all like binary is, but this output here is. Let's go ahead and show what it does. If we have an output of 0, we get 0. If we have an output of 1, we get 1. Here, the least significant bit is here on top. Most significant is on bottom. Kind of got switched up between the two. We can add 2 here, and we get an output of 2. As you can see here, we have 1, 0. Doesn't matter in what order, 1, 0. Now let's have all 3 on, and we have an output of 3. 1 plus 1 plus 1 is equal to binary 3, 1, 1. So now here in adder 4, we're going to combine, in this, we're going to have 4 full adders together. And what this will allow us to do is add 2 4-bit binary. So here we have our first A3, A2, A1, A0 from most significant to least significant, 1 set of 4 bits, and then B3, B2, B1, B0 is our next 4 set bits, and we will be adding them together. Here the Cin, this is going to be left in at 0 because if we were to say have another 4 full adders before this and had a carry out from that, it would go in here. But right now this would be the start, so we're just going to leave this as 0 or as ground. Can also be represented as ground. So I'll insert some bits here. For A, I'll go 1, 1, 0, 0. For B, I'll go 0, 1, 1, 0. So as you can tell, we have 0 plus 0 gives an output of 0 and a carry over of 0. This is where carry outs happen, and we'll get to it over here. Here, A1 and B1, 0 plus 1 comes out to B1 with the carry out of 0. And here, A2 plus B2, we have 1 plus 1, which is gives an output of 0, and then the carry out is equal to 1. So we'll have here in the Cin a value of 1 plus 0 plus 1, which gives us 0 here, and a carry out of 1. So there we go. That's our answer. So, and now we have here the same circuit here, but completely condensed down into a smaller sub-circuit. All our inputs are here, all our outputs are here, and it will give us the same exact result. Let's see, what was it? It was 1, 1, 0, 0 for A, and then 0, 1, 1 for B. Yep, 1, 0, 0, 1, 0 is our answer, which was here, 1, 0, 0, 1, 0. So that shows that in working condition. Question for the professor was, I had trouble getting these 4 bits into a single 4-bit input and having each bit respectively go into B0, B1, B2, B3. Kind of like, let's see if I can pull this here. Kind of like what you had here. I was having trouble getting this to look very nice like you had it. So I'll probably ask you that on Thursday, excuse me. But yep, for now, that is it. Thank you for watching.